Hi, okay. I suggest that we start. Okay, so last week we started talking about how to treat interaction terms in a perturbation theory. And the main problem we have to solve is, suppose we have some single body Hamiltonian. We know how to solve it, we know how to diagonalize it, and we also know the ground state, or any state, any of the eigenstate. And now the problem we want is to see what the interactions are doing, and the first and simplest thing to try is to do perturbation theory. And from that, we need to know how to compute expectation values of operators, which we write in the second quantization language. So today we are going to first introduce a theorem that is called the Weeks theorem. And this is a tool that is often used in this context, and I'm not going to prove the theorem. It's a mathematical theorem. Actually, I think Sar is going to do it on the next tutorial. But what I want to just state it, and we're going to work with it, okay? So we'll treat it as a given. So first of all, I want to remind you what is the problem we have. And we have some vacuum state, and by vacuum state, I refer to whatever we want to treat as a vacuum state, okay? And it may be, for example, the ground state of the non-interacting part of the Hamiltonian. And with respect to this ground state, we have some set of operators with various lambdas, annihilation and creation operators. And well, the lambdas run over all the possible quantum numbers or quantum states of the non-interacting problem. And the annihilation operators are defined with respect to this vacuum state. So they're annihilated. And any operator in second quantization can be written as a product of a lot of operators, A, B, C, and so on, where all of these are belonging to, so A, B, etc. belong to this set of operators.
So they only can be השמדה ויצירה?
Yes, they can be any arbitrary string built of these ingredients. It can be A1 dagger, A2 dagger, A3, A4, A5, A6 daggers, and so on. Okay?
Or with every kind of operator, or some
Every-
operator?
Okay, so I think we discussed it,
Yeah.
or maybe you asked it last
I
time.
think.
Of course, the more general type of operator is a sum of such things.
Okay.
But if it's just a sum, then if we know how to compute expectation value of one term in the sum, we know how to do the sum. Okay? So I'm focusing on a set of operators of this form. And I defined, this was at the end of last week, I defined a quantity called normal order of O. Okay, and that's actually write it before. Normal order O we define as, we put these two columns, and the definition is a reshuffling of the string so that you get zeta to the power p times a product over some lambda primes of a dagger and a prime, and the product of lambdas of a lambda. Okay? And what is this factor zeta to the p? So if we take a general string and we want to bring it to this form, we have to exchange, to do some permutation, right? When we do the permutation, each permutation between different quantum numbers will give you, I mean, according to the commutators or anti-commutators, will give you a factor of zeta to some power, and this power is the parity of the permutation, basically, okay? So, yeah, let us just remember that zeta plus minus is bosons, fermions, and this is what encodes the statistics in our course. Okay, so that's a normal order, and it is easy to see that the vacuum expectation value of the normal order form is 0. Okay. By the way, an arbitrary operator may have only creation operators. Okay, that's also a subset of this form, right? I can have an operator that is combined only of creation operators. Okay, so why is the vacuum expectation value of that always 0? So we know that A acting for any lambda, A acting on the vacuum gives 0. Okay? A dagger acting on the vacuum will not give 0, it will create a particle, but when we compute an expectation value, so the expectation value in a vacuum state,
it will work on the other side.
It will work exactly. It will be the emission conjugate of that, right? So therefore, no matter how many daggers and non-daggers you have in the form, this is always 0. Okay, and because of that, if we take an operator and subtract from it the vacuum expectation value, it will essentially give the normal order, because we are interested in anything that contributes something above the vacuum. Okay, so the normal order is a good way to represent the non-trivial part of an operator, because if the vacuum is, let me put it this way, there are some operators that may have a finite expectation value in the vacuum, but this is not interesting. It's like ground state energy, it's some constant, and we're looking at excitations about it, okay? And particles, we think of particles as excitations above the vacuum. Okay, so that's just a definition. And under this definition, there is something interesting that I can say about a special case where O is just the product of two operators, A and B. And again, A and B are anything, any combination of A and A bigger, but just two of them, okay? So let us see what the normal order is going to be for the case of just two operators of this kind. And I'm taking this as the definition. So any operators, to bring it to this form, you need to reshuffle to exchange the order, and you may pick a factor of minus. So there, if you just have two operators, there are only two possibilities. Either they're already in normal order. Okay, if they're already in normal order, the normal order and the operator itself are the same, right? I don't need to exchange anything. So AB normal ordered equals AB if already normal order. Okay? And now, if it's not normal order, we need to make an exchange, but there's only one exchange. So it's going to be BA times a factor of zeta. Why a factor of zeta? Because it's an odd operation. Okay, we just exchanged once. And therefore, okay, there's a factor of zeta. Okay, if not. Okay, there are only two options. Okay. Now, okay, so as a result, let me now define the following quantity. AB, okay, and this notation, I call it a contraction. I denote it by putting such a clip on the two operators. And this is the definition. It's AB itself minus the normal order. Now let's see what it gives in either of the options. So in the case where AB was originally already a normal order, what does it give? Zero, right? Okay. If it's not, then I get AB minus zeta BA. But what is this object? This is either commutator or anti-commutator. Okay, so this thing is either AB for bosons or curly AB, the anti-commutator for fermions. So if you like, there are actually three options for what this object can take, but what I can say about all of them is that it's just a C number, a constant, right? it's either 0 or, and remember, A and B are just one A and A dagger, all these options. There are 4 options, if you like. And each of them gives you either 0 or 1, right? Because we know that these are the basic commutators defining the creation and annihilation operators, the algebra, okay? So, therefore, you see the contractor is no longer an operator at all. It's just a number, okay? And why is it important for us? Because if I want to look at now the vacuum expectation value of AB, of the operator AB, is going to be, if I'm using this definition, I can write it as the vacuum expectation value of AB normal ordered plus the contractor, right? But what is the vacuum expectation value of the normal order? 0, right? So it is actually just the contractor. But the contractor is a number. It's a number, right? So any number, any C number, I can take out of this expectation value. And I get AB contractor times the overlap of the vacuum with itself, which is 1, okay? So in short, what am I getting from this? I get that the vacuum expectation value of any product of 2 operators A dagger is equal to the contractor, okay? Okay, so now let's, and we know what is the contractor because it's either just 0 or the commutator anti-commutator, okay? Okay, so this is an important formula, and let us see what we can get from it. Let's look at special cases, because I said that these A and B's are, any of them can be A or A dagger of some index. So a product of 2 can be either of 4 combinations, okay? It can be A dagger, A dagger, A, okay? Let's check all of them and list them and see what they give. Okay, I think this I can already erase. Let's just leave this contraction. Okay, so let's look at, and by the way, I want to also introduce another notation just for shortcut of the notation. Instead of writing every time expectation value in 0, let me just denote it by these angular brackets. Okay, so this is just a shortcut for a vacuum expectation value, okay? At least in this class, okay?
And by vacuum,
just
ground state.
Whatever it is, yes. It doesn't have to be the one set, by the way, but it is the vacuum for which, with respect to which, A and A dagger are annihilation or creation. Okay? That's the most general statement. Okay, so let's see. So what are the options? As I said, there are only 4 options. Let's first look at A lambda A mu. What is this? And again, this is what we have to account for. It's just a contractor. What is the contractor in this case? If both of them are annihilation operators,
0.
it's 0, right? Because it's already normal ordered. I don't need to switch anything. So this is 0. Similarly, this, for the same reason, this is also 0. Okay? How about A lambda dagger A mu? What is this?
0.
Also 0. Why is it 0? Because
Annihilation operator.
it's already normal ordered, right?
It's making annihilation on the vacuum state.
Yes, that's exactly right. Yeah, that's exactly what you have used, in fact, to get this. So all of these are 0. What is the only thing that can be non-zero?
A dagger.
Exactly, because then you'll have to reshuffle, and then you'll get the commutator or anti-commutator. So A lambda, A mu dagger, that vacuum expectation value is not 1, not necessarily 1. Now it depends on lambda mu. It's delta of lambda mu, and this is correct for both fermions and bosons. That's very important. For 2 operators, there's no distinction between fermions and bosons. Okay? Very good. Okay, so we know how to calculate any expectation value of any two operator combination, but this is not so useful because this we already know. This is a one body thing. But what we want to be able to compute is interaction terms. In the typical interaction term, the simplest one we have, which is a 2-body interaction, there are 4 operators. Okay? So what do you do then? And that's where the Weeks theorem will apply. So I'm still not writing the theorem, but let me first make some definition, another definition. So suppose I now look at a normal order of I don't know, so let me, X, Y, Z, okay? And now I take out of this string, I put the contractor sign between 2 operators, okay? Which are somewhere in the middle, C and X, let's say, in our case. What is the definition? So what is this? We know what is a normal order before the contraction, right? It's just reshuffling all the A's to the right and putting some Z to the P, zeta to the P. But what is this? So let me define. So it's a contraction of 1 pair of operators out of a long string. And the definition is that you extract from the normal order, you extract Cx contractor, which is just a number, and put here zeta to the power p, and then what you're left with is A, B, and now C is missing, and also X is missing, and Y, Z. And this remains like a normal order operator, okay? And this is a definition, and the idea behind it is that the operation you need to do from here to here is to take these two operators, reshuffle them to the left, okay? And when you do this reshuffling, you pick up some factor of zeta to some power of the permutation, and then you contract them, okay? And then the contraction is just a number, okay? That's the definition, okay? Clear? That's just a definition, okay? I can give you a simple example. Suppose I have something like that. I don't know. Let's say, okay? And I want to see what is the normal order of this. What is it? So I and I put the contractor here, okay? Actually, let me, okay, never mind. Let's give them some lambda prime, mu prime, just for example. So what is the meaning of this? I first of all, I reshuffle this through here once and this through here twice. So overall, it gives me a factor of zeta, if I didn't make a mistake, times the contractor of these guys, which is a delta of lambda prime mu, and I remain with a lambda dagger a mu prime, normal order, okay? That's just an example, okay? Okay, so under this definition, I can now, so let me erase it because it was just an example. I can, of course, repeat the contraction for another pair, okay? And again, I will get a phase factor times a contractor, and so on and so forth. So, in principle, if I have an even number of operators, I can always contract one pair, another pair, okay? And when I'm done with all of them, I just get a number, okay? So, for example, something like, let's take the same string, but now I put one contractor here and another contractor here, okay? What is this? It's going to be zeta to some one power, zeta to some other power, doesn't matter what they are, times bx contractor, cy contractor, and the remaining a to z. Okay? So here I'm missing the b, c, x, and y, and okay? Okay, so what does the weak theorem say? I hope you're going to prove. I can now, actually let me, I think I can erase it, right? I need the space, and if necessary we'll bring it back. So, the weak theorem states the following: for any string I can express as a series. I can expand any normal order of any operator as a series of terms where the first term is just sorry. No, that's yeah, forgot. This is the operator itself. So any operator, that can be written as a string, I can write as an expansion. First, the first term will be the normal order of the whole thing, plus a sum over all the pairwise constructors of normal order x, y, z. Okay, well, what does it mean? I take this operator and I contract one pair. That's one term. But then here I have many pairs. So I'm summing over all the pairwise contractors. And I write it like this. The next term in the expansion is going to be a summation over all the double pairs, okay? All the pairs of pairs that I'm pairing, I'm contracting. And this is an infinite series, and the last term, okay, actually it's not infinite, sorry. It's, the last term is summation over all the pairwise contractions I can do, which exhausts basically the pairing, okay?
So it will be just constant.
So exactly, the last term is just a number, okay? Now, because this is true, what can I say about the vacuum expectation value of O? Okay, what is the vacuum expectation value of O? It's basically, I put each of it's a sum of expectation values of all the terms, but all the terms except for the last have zero vacuum expectation value because they contain a normal order of something. Okay? So the only term that survives is the last term. Okay? So that's what the Weak's theorem states, that the expectation value of any string operator is a sum over pairs of let me write it, yeah, it's a sum over pairs of well, zeta to some power times a product over alpha of A alpha, B alpha, okay, contracted, okay? So, so the alpha is a pair. Okay, so out of the string I have, I can do a pairwise constructors of all the possible combinations. When I'm done, I'm getting just a product of the constructors times a phase factor. And that's true for any choice of pairing, okay? So I'll give you soon a simple example, and then we'll see how to work with it. But that's the general expression.
Question.
Yes.
I get it that the reason that we do the expectation value to the vacuum state because in folk space we can always call the express the early state in terms of the vacuum space.
Yes.
So
that's
effectively,
right.
effectively
That's right.
when we look at the Hamiltonian, we don't look for the energy. We will not actually look at the expectation value for example, for one, but
yeah, well,
for,
the one operator will never have an expectation value, right?
Yeah.
It's not a physical
Yeah,
operator.
it's not for that, but so we'll want to express the one operator for in terms of the vacuum operator, and the new operator will be the one that we will use the Weeks theorem on.
Exactly,
Okay.
exactly, right. So, but actually I should have one step before, here I wrote an arbitrary string of operators, but there's one case in which, without doing any calculation, we know that the answer is 0. If maybe I should write it a little more carefully, okay? So I can divide it to two cases. One is if the string contains odd number of operators, I always get 0, right? Because when I contract pairs, always one operator will remain unpaired, and its expectation value is 0, okay? Right?
So the last
so
term
any odd string, if I do this,
the last term will not be a constant, right?
It will not be a constant. That's right. That's right. Okay. So so I get 0 if number of operators is odd. If the number of operators is even, then I get just what I wrote before, which is the sum over pairs of zeta to some p times product over the contractor, sorry, A alpha, B alpha. And that's what the Weeks theorem tells you. And actually, sorry, I forgot to write this product of contractors. Okay. Or and because of this formula, these contractors are nothing but the vacuum expectation value of the pair AB. So another way to put it is that, let me just write it in the shortcut notation, the vacuum expectation value of O is a sum over pairs. It's not, actually when I write sum over pairs is pairings, okay? So it's, in each term I'm choosing some combination of pairs, okay? So it's sum over pairings of zeta to the p and then I have just, sorry, a product over the pairs in that pairing possibility, sorry, expectation value of A alpha. Okay, so let's put this in the box. Right. Okay, and in particular, let's take an example. Before I come to a concrete example, let's just take an arbitrary 4-operator combination. So let me erase this. So and again, this is true if this is an even, if there is an even number. Otherwise, immediately see that you get 0. Okay, or 0. Okay. So let's take an example. Suppose I have, let's just take A, B, C, and D. So in this moment, I'm not saying anything about how many daggers and non-daggers I have, just 4 operators. I want to apply this theorem. So when I'm looking at only 4 operators, there are only 2 different ways in which I can divide them to pairs, right? Either this is one option, okay? The second option, I use it with a different color, is this and this. Is that right? Let me see. Is there another option? Ah, sorry, there's a third. Sorry. Very good. No, there's a third one. There's a third one. In a minute you'll see why I neglected. So let me draw it down here. Although it can pair this with this. It's a different one. Okay. So 3 options. Okay. Let's write them explicitly. Let's write explicitly what I got here. And let me use, I want to be consistent with the colors that we keep track, yeah?
3 and not 4 options?
There are no 4 options. What is the, because if I'm looking at the operator A, I can pair it with any of the other 3. Once I do this,
okay.
So there are only 3 options.
The first one is known.
The first one is known, and then okay. So only 3 options. Let's start with the red option. The red option. Notice that when I write it as a product of the two contractors, I don't have to reshuffle anything, right? Because I don't have to exchange them in order to put one next to another. So there is no factor of zeta. Okay? So it's just AB times CD. That's the first term. Okay? Okay? Second term is the blue. The blue one, I contract A with C, but in between them there's one other operator. So I need to exchange B and C in order to bring it to this form. Therefore, I pick a factor of zeta, and I get now a product of A and C, B and D. The third option is to contract A and D and then B and C, okay? But actually, I can do the B and C first, but maybe it's easier to see. Let us contract A with D first. In order to do that, I need to reshuffle D 2 places to here, right? But then there's an even number of permutations, and therefore there's also no factor of zeta, right?
Mm-hmm.
So this comes with a plus without any zetas of AD and BC. By the way, notice then that in each of the contraction, I keep track of the order of the 2 operators. So it's AD and BC, not reshuffling anything, okay? So this is what happens for the case of 4 operators, okay? And you see that it's actually quite interesting, quite simple. It becomes very simple because, as we said, all the pairwise expectation values or the contractors are just either 0 or a delta function, and the delta is obeyed only if you have an A and A dagger of the same quantum number, right? So we have a very simple prescription to compute the expectation value of a four operator string. If it's already 6 operator, there will be more terms, but we mostly care about this kind of terms. Why? Because in a 2-body interaction, that's what you have. Okay? Okay, great. So let's now take a physical example. Okay. And now let me just write this formula here. Okay. All right, so the example I want to discuss is interacting. So this is interacting fermions. Okay. Okay, so I have some fermions, and I have the 1-body Hamiltonian H naught is diagonalized in some basis lambda. And I know that its ground state is a Fock state, a Fermi C, where I occupy all the states up to the Fermi level, right? This is the ground state, which we call the block. So this is Fermi C is a product of lambda belonging to F of a lambda dagger acting on the, okay, I don't want to call it a vacuum, let me call it, I don't want to call it let me write it like this, okay? So that's like the empty vacuum, okay? But, and the definition of this is that epsilon lambda is smaller than the Fermi energy, okay? So this is the ground state of the system, and now I imagine that I have some interaction operator, which is the most general form of a two-body interaction is summation over 4 indices of V lambda lambda prime mu mu prime just keep track of the order, not to get confused. Yes. Yeah. A mu dagger, A mu prime dagger, A lambda prime, A lambda. Okay, this is the most general interaction, two-body interaction term. And what I would like to do is perturbation theory on this term to first order. In the first order perturbation theory is just an expectation value of V interaction, but not in the vacuum, in the ground state, right? So in other words, we imagine that we have already a vacuum, a ground state of the non-interacting. We solved it. Now we want to add the interaction and see how they correct the energy. That's the calculation. So this is our goal. We want to compute this expectation value. And to do that, let us now define our vacuum as the Fs state, okay? So, so this is the first step we do is we take this guy and we call it a vacuum, okay? But now we have a problem because, not a very complicated problem, but there is a problem we have to worry about, which is our interaction is written in terms of operators A and A dagger, which are defined with respect to this vacuum. That's not good, because then if we want to use the weak theorem as we just learned it, we need to switch to new operators that will serve the role of the true annihilation and creation with respect to the new vacuum, okay? What are they? We defined them last week. They are the operators that I denoted by C instead of A. And I remind you the definition is that C of lambda is, let me write it in a shortcut notation, is 1 minus theta A plus theta lambda of A dagger. Okay? This is, okay, remember we proved it last time. What is the definition of A lambda F? Maybe I denoted it using different, I think okay. Never mind, let me just define it. What is this theta? It's very simple. It accounts for the question whether lambda is inside the Fermi sea or outside. Okay? So if it's outside, If it's an empty state, then C and A are the same. If it's a field state, but it's a fermion field state, then the creation operator A dagger will annihilate it. Okay? Right? That's where it comes from. And this is just a theta function of epsilon f minus epsilon lambda. It's the step function, okay? Which is, okay. You know, this is 1 for theta of x is 1 for x positive and 0 okay? Okay, that's what it is. Now, I can also write down the inverse transformation. So I can express A's and A daggers in terms of C and C daggers. What is the inverse transformation? So in principle, you can think of it as a special case, a very simple special case of a superposition, right? And there's some unitary matrix relating them, and but because it's only 1 or 0, the inverse transformation is actually looks exactly the same. So it's this, okay? So A is a combination, or it's in fact not a combination. It's either a C or C dagger of the same lambda, depending on whether it is inside or outside of the Fermi C. Okay? Okay, so so that's what I have, and now therefore I can now express what I want to do is to compute an expectation value of this 4-operator string using the Weeks theorem. As we see here, there are going to be only 3 terms, and each of them is a product of contractors. So the first thing I want to know is what is the contractor using the fact that I have to switch between A and C, okay? So let's check all the combinations, because once again, there are only 4 options. A dagger, A dagger, A dagger, A dagger, but they're not going to be the same one we wrote before, because that's true for the vacuum. Now we have to first convert them to C and then use it. So, okay, so let's check all the 4 possibilities. First, the simplest one is any combination of 2, okay? Sorry, it's 2 annihilation. What can I say about it?
0.
It's 0, right? Why is it 0? First of all, so lambda and mu can be either the same or different. If they are the same, that's immediately 0, because it's a fermion. A square is always 0. But if they are different, then in order for this to be non-zero, we need to have that lambda is inside, okay? Lambda is inside the Fermi C, and mu is outside. But then the answer will be delta of lambda and mu, and the delta is also 0, right? So in other words, if the indices are different, and if they are the same, in either case, we get 0. So this is 0, and of course, trivially, the same is true for the expectation value of 2 daggers. Now we need to check the combination A lambda dagger A mu. Okay? And actually, I also need to check A dagger, but I actually don't need to do that. Why? Because as you see, the particular string I'm interested in is already written normal ordered in the A's, okay? So in fact, when I apply this calculation, I will not need to reshuffle A and A dagger, okay? I can do that, and there's an answer, but for our purposes, we don't need it. It will not come out in the calculation. So let's see what is it. I'm using this transformation, the second line, and of course, its Hermitian conjugate will put, let me write it explicitly, so A lambda dagger is the same factor of theta 1 minus theta C lambda dagger plus theta of C, right? Okay, now when I plug in the transformation here, I get 2 terms that do not vanish, which are, because you see that every combination, in principle, I have 4 terms, right? Because I have a product of 2 terms with 2 terms, but 2 of them are vanishing because any combination of C or C dagger will vanish, okay? So the only 2 terms are either you have both lambda and mu are outside of the Fermi C, in which case this is just C dagger lambda C mu, right? That's the case where we keep track of the same. C, A, and C are the same, of the same nature, plus the second term will be if both of them are occupied, both lambda and mu are inside the Fermi C, in which case we have C lambda C mu dagger. Okay? Okay, let's see. You agree, right? Now, with respect to our vacuum, now C and C dagger behave like, really like annihilation and creation operators, namely, the expectation value of the first term is 0. So therefore, I'm left with only 1 term. And its result is a delta, right? So this is delta of lambda and mu. And therefore, we have here a simple formula that, let me just repeat it. So, A and A dagger gives 0, while A lambda dagger A mu gives the a delta of lambda mu times the product of these thetas. But if lambda and mu are the same, I don't need to repeat it, right? So this factor is either 1 or 0, depending on, let's say, where lambda is occupied or not. And in fact, what is this theta? What does it tell us? We have a Fock state where I fill all the states below the Fermi level, and this gives me either 1 or 0. It will give me 1 when the state is occupied. Okay? So, so let me, first of all, let's put this in the box, because this is what that is all we need for our calculation for now. And the physical interpretation of it is actually very simple, because we get a non-vanishing result only if lambda and mu are the same. But if lambda and mu are the same, the operator that appears here is nothing but the number operator. Okay, this is for the case for lambda equals mu, which is the only one we care about. And therefore, what is this theta? Is we can just call it n lambda without the hat, because it's just the occupation of the state lambda in the non-interacting Fock state. Okay. That's all it is, okay? And, okay, very simple. And now we can go back to our Week's theorem and apply it to get a closed expression for the expectation value of the interaction, okay? This is exactly what we wanted to achieve here. Okay, so let's write it down. And I'm writing it as expectation value under the convention that expectation value is expectation value in the vacuum, and that the vacuum we're talking about is Fock state, okay? A field Fermi C. So this is what we get. First of all, we have a summation over many contributions. There is a sum over lambda prime, mu and mu prime of some coefficients of the interaction matrix elements, these guys. And now we have to take the expectation value of a product of these four operators. Okay, so write it like this: mu prime, a lambda prime, and a lambda. And now let's see what this gives. And I use the expansion that I wrote here because I can put my contractors, let me follow the same colors, okay? So the red option, okay, there are three terms. The red is this and this, okay? What does it give in our case? 0. Okay. The blue one is this and this, and the purple one is this. Okay, and now let me write down the two terms. Actually, now that I'm looking at my choice of colors was not good, but we'll have to stick with it. The reason it's not good is because it's not consistent with the notes I published on the Lambda, but let's stick for it now. Too late to change. Okay. Now let's write them down explicitly. Okay, so the first term is the expectation value of A dagger times AA, that's 0. Okay, it's coming from the red. Okay, second term is the expectation value of the A dagger mu and A lambda prime, but notice that now there's a factor of zeta. But what is zeta for fermions? It's a minus sign, okay? So there's minus A dagger mu A lambda prime times A dagger mu prime A lambda. And by the way, I already tell you that the fact that this term, which has the zeta factor in it, is quantum, okay? I mean, it's a term that cannot have a classical analog. If we think of some mean field theory of a classical interaction term, we cannot have factors of minus because of the statistics, okay? So this minus sign is very important, and it's special to the fermions. And now the last term, which also comes with a plus, is A mu dagger A lambda, A mu prime dagger A lambda prime, okay? And now let's take this and get the final result for the interaction. So V interaction expectation value is 1/2 sum over lambda lambda prime mu prime, and now I already have a formula for these expectation values of each pair, right? And notice that they have some deltas, and then summing over them, I will be able to get rid of 2 indices in each time. So let's write down. So the first is 0, I throw it away. I have 2 terms. Let me order them by taking first the positive minus the second, okay? So the first one is A dagger mu A lambda. What is it? It's a delta of mu and lambda times a delta of mu prime and lambda prime times the occupation of lambda and the occupation of lambda prime. Okay, or let me write it. So we can actually combine these two terms together if I put the combination of deltas inside the brackets and take out the factor of theta mu and theta mu prime because they are common to both of them, right? So let me write it down and you'll see that it's correct. So here I have a delta of mu and lambda prime, delta of mu prime and lambda, and all that is multiplied by the theta of not of lambda, because if I want to stay consistent, it has to be mu and mu prime. Right? Okay, you agree? So again, this is, and these thetas are nothing but occupations. Okay, I can just call them, if you like, occupations. Occupations in the fog state, in the ground state. And so they come out in both terms, but then you see this is not zero, it doesn't cancel, because one time I have a delta equating mu to lambda, and here it's to lambda prime, okay? So if I use the deltas to eliminate the indices lambda and lambda prime, what I get is, and this will be our final result, a sum over only two indices, and the indices will be mu and mu prime. And sorry, very important. Sorry about that, I forgot something very important, the coefficient v. Okay, otherwise this would give me 0. Okay, so let me bring it over here. V of lambda prime, mu and mu prime. Okay, so now here I have the occupations, but when I apply the deltas over the indices, at one time I'm equating mu to lambda and mu prime to lambda prime, right? So the positive contribution gives me V of mu prime and mu prime, okay? So two indices repeat themselves in the same order, minus V of what is it? So it's mu prime. Wait, yeah, mu prime. But then I have mu prime and mu. And this is all multiplied by the occupation of mu and the occupation of mu prime. Okay? That's the final result. Okay, now I want you to look at this expression, and first of all, you see that it's very simple. I mean, of course, there's a summation over a lot of terms, but now you sum only over two indices, and you only get contributions from occupied states. Okay, so the expectation value makes sense. Only the particles that exist are interacting, are contributing to the energy. But what is most interesting, if you look at the order of indices here, what is the difference between the first of all, they are not the same, right? Generally, they're different matrix elements of the interaction, so it's not zero. What is the difference? If you go back to what we did last week, the first term is what we call direct or Hartree, right? Because it's we defined it on a lattice, so it was ij, but it's the same. Okay, the mu here is some general index. So this is direct or Hartree. And the second one, which comes with a minus sign, and that's what, erase this, this is what we call write it more conveniently. So we got that. Just copying it so it will be easy to say. So this is just 1/2 the sum over mu and mu prime of the occupations times V mu prime minus V of mu prime mu. And this is called the direct Hartree. The second one is exchange or Fock. Okay? And the difference between them is that in the second one, we are exchanging the order. Okay? And notice that there's a relative minus sign, and the emphasis that I emphasize, this is for fermions. For bosons, it will be a plus. So they will add up, and in a sense, that will make it a little less interesting. Okay? Okay, great. So this was for a general interaction term. And now let's take a concrete example for a physical problem with interacting fermions, where this can be applied. And in principle can be applied to do perturbation theory. And that's the problem of a metal or a conductor, just a free electron gas, where we put the Coulomb interactions. Okay? That's just a physical application of this. And what I'm going to do now is to define an approximation scheme that we call Hartree-Fock. Okay? And of course, you can use it for a general set of quantum numbers, mu, lambda, and so on. But I'm going to demonstrate it for the particular case of Coulomb interactions in a metal. So let me erase this and so actually yeah. Oh, okay. Let me, before I do this, let me take just 5 minutes and then we'll make a break. I want to define the more general case of Hartree-Fock approximation. So let us again stick to the general interaction term, and I now want to make an approximation not on the expectation value, which is the final result of some perturbation theory, but on the Hamiltonian. Okay, so I have a general Hamiltonian, H equals H naught plus V interaction, and I want to replace it by an approximation, which I call a Hartree-Fock approximation, where the Hartree-Fock will be the same H naught. I don't touch it because this is already simple and we know how to diagonalize. But the interaction term will be replaced by some approximate form, and it's an approximation for the real exact problem. So what am I assuming? I'm assuming that the corrections are small. Okay? Namely that V interaction and V Hartree-Fock are close to each other up to some correction. And the nature of this approximation is very much like a mean field approximation that I believe you already saw in statistical physics, right? That you have, for example, some Heisenberg model, and you have an interaction S dot S, and you replace one of the two interacting operators by its expectation value. It's called mean field because you are replacing an operator by its expectation value that averages over the fluctuations of the environment. Okay? Now that's a good approximation if the fluctuations are small. Okay? In the statistical physics problem, the fluctuations you're talking about are thermal fluctuations, okay, that come from statistics, from the standard deviation. In the quantum problem, there are quantum fluctuations, okay? But in various cases, it is justified to assume that they are small, and therefore this is a good approximation to the real problem, okay? So what is the idea behind the Hartree-Fock? Any set of operators of this form, where I have a mu dagger, a mu prime dagger, a lambda prime, a lambda, that's one of the general interaction terms that I have. I'm replacing it by a form that out of the four, I take two operators and replace them by their expectation value. But I have different options how to do it. In principle, I have three. Okay, I can replace a dagger by expectation. I can replace a dagger A and a dagger. And the first option, a dagger, expectation value is 0. Okay, So, but let me write it down anyway. And actually here, I also have the, I can leave out these guys and put the expectation value on the annihilation. Okay, but this is anyway 0 in our case. So I don't care about it. What I do is mu dagger a lambda prime. Actually, okay, just for, okay, let me do it like this, a lambda prime, sorry. A mu prime, a lambda prime, minus, and this minus is because of the fermions again. So this is the exchange, which is a dagger mu a lambda prime, a mu prime, a lambda. Okay? And now actually in principle you also have you can put the expectation value on the second term. We'll see that this is counting twice the same, because eventually we are going to sum over all the indices, and it's enough to keep just one term like this. Okay? Okay, so I'm writing this as this is 0, but keep in mind that later on in the course, I think maybe 2 lectures from now, you're going to see an example of a physical problem where I have to define a new vacuum such that these are not 0. Okay? So just bear it in mind that it's not to be taken for granted. But these ones that we keep, and we call them, this guy is the Hartree, and this guy is the Fock. Okay? Now, why is this approximation useful? Because notice that the approximate form replaces 2 of the operators by a number. Okay? So altogether, V interaction Hartree-Fock is another single body type of term, right? It has only one pair of A and A dagger. And this number will be combined with the coefficient, the interaction coefficient, will just give me a matrix element. It will give me a term in the Hamiltonian, a constant, okay? But the Hamiltonian, maybe we'll have to re-diagonalize it. Actually, in the example that I will give for the interacting electrons in a metal, this even is not, you don't even need to re-diagonalize it. It will come out to be very simple, but it's a single body. Okay, so it's exactly the same idea as mean field in a magnetic system. You are replacing your other particles by some average, okay, some average field, and that's just a term in the single body, effective single body contribution. Okay? So let's take a break until 6 and we'll continue.
בסדר, היה לי מפגש עם המנחה שלי היום.
כן.
בסדר. איך הולך המחקר שלך?
בסדר, מצוין. שאתה יודע. תראה.
אני מציג את זה בעוד שבועיים. כאילו מציג את זה בלי מילים, אבל אני הולך להסביר הכל.
אוקיי. כן, כי כמו התיאוריה קצת קצר, זה רק מצגת אחת.
כאילו יש קפיצה שהיא יכולה להיות מעבר פס.
רק שווה לעשות לייבלס ומה זה אדום, מה זה כחול ומה זה שחור.
כן, אז אולי אם אני אסביר את זה או שאני אסביר את זה. זה כאילו פשוט זוויות פולריזציה שונות של צדדי חשמל.
כן. זה free energy?
אמפליטוד.
כן, גם פה יש כזה, יש second order, phase transition.
נכון. second order. הכל רציף.
רציף, אז פה זה נהיה כזה. מה זה מודד? זה
הדלתה.
כן.
מולטי קומפוננט של איכות. כאילו פה בעצם מצאתי תיקון לפי תורת ההפרעות של האחרונות. זה מיותר, כאילו זה כל מיני נקודות אחרות.
And it's the first order expansion.
כאילו אתה לוקח את הלמונה,
כן, כן, אני זוכר, למדנו את זה באחד.
אתה לוקח את האנרגיה החופשית, סדל פוינטס, ואז כאילו פה אם שבגבול הזה יש לך ערך שלילי כלשהו, בגבול הזה יש לך ערך חיובי כלשהו, וזה מעבר רציף.
זה בעצם אותו דבר שרק קצת יותר...
רק עם פרמטר
כן.
בטא שהוא לא אפס. לא איתך. וואלה, בסדר.
כן, אתה מוסיף שזה חשבוני שכזה דרך מזמן.
כן, לא איתך.
וואו, זה ממש...
כן, עכשיו תראה אם אני מגדיל את הדם.
אוקיי, הגיוני האמת.
התחלת ללמוד למוחן בסטטיסטית?
יש מה לגמול?
כן, זה רק...
קצת, שיש מה
אני
ללמוד.
רק אעבור על
על
הקלקולי בית ועל השנה.
יש לי סיכום, שלחתי לסטס שיענה כאילו לאתר. שאני כתבתי, אם אתה רוצה.
אפשר לך בקבוצה, יש לך קבוצה.
כן.
אתה לא בקבוצה?
נראה לי שאני כן.
יש
כאילו זה...
קבוצה גם של תארים שניים וגם של...
נראה לי זה קבוצה. הוא לא בקבוצה.
לא בקבוצה? זה בתוך הקומיוניטי כזה של...
באמת?
כן.
כאילו אני בקבוצה הזאת, אבל אני לא בשאר. אין פה. מה אתה חושב?
כן, האמת טוב.
נראה טוב?
כן.
עכשיו איך לעשות אותך. לשתות קפה.
לא, אני בסדר. גם לא נשארו כוסות.
מה אתה?
כן.
באמת?
אין כוסות חד פעמיות.
או.
לא. בדרך כלל בימי חמישי כבר נגמרו כזה מתחילת השבוע.
אמרתי להם לשלוח קישור לקבוצה סטטיסטית. סבבה.
אם אתה רוצה אני יכול לעבוד לך בוואטסאפ? כאילו ממש סיכמתי את כל הדבר. ואם אתה רוצה כאילו, אתה יודע, נעשה
יש הרצאות או של גלגלים? יש פה עוד הרצאה?
כן.
מתי?
כמו עוד כמה דקות, כמו עכשיו אנחנו בהפסקה כזאת.
בקיצור, הבישול היה נפשי, לא יודע מה מפה בארץ, ברוך הלכנים. לא תגיד.
השיעור?
עד 7:30.
וואו, אתה רוצה לתפוס לך שיחה.
לא היום.
ביי.
מ-5 בבוקר עד הרגליים.
5 בבוקר.
ואני צריכה לנסוע לחיפה מיד אחרי זה.
בסדר. יום ראשון? תהיי פה?
כן, אבל אתה זוכר שביום ראשון גם קבענו... לא, זה שיחה, פגישה מאוד חשובה, ב-4.
ב-4?
בזום.
בזום ב-4. כן, אני יודע שזה מאוד חשוב.
אם תרצה לדבר לפני...
בסדר, כן, אני אולי אכנס לך לפני. ביום ראשון ב-4, בסדר, אני פשוט... בסדר, זה סופר חשוב.
כן.
טוב, ביי.
אז ביי. Okay, I think I would like to start. Please come in. Okay, so now we'll go to an example of application of this Hartree-Fock approximation, and this is the case of electrons in a metal, where we have the free part of the Hamiltonian is just kinetic energy. So the quantum numbers lambda are the wave vector and the spin of the electrons. H naught is just a sum over k and sigma of epsilon k, a dagger k, sigma, a k sigma, and the interaction is here. Is the Coulomb interaction, but if I write it in a more general form, it can be expressed as a sum over 3 indices of wave vector and 2 spin indices. And And here we have VQ, which is the Fourier transform of the interaction in real space. For Coulomb interaction, I remind you that V of Q for Coulomb is 4 pi E square over Q square. It's the Fourier transform of the function 1 over R in 3 dimensions, but 3D. But this is just an example. Let us keep it simple and keep it general and call it V of Q. And then this is the convention how we write it. There is a summation of, as I said, 3 indices. And here I have, I want to write it like this. Sigma. A dagger of K prime plus Q and sigma prime, A of K prime and sigma prime, A of K and sigma. Okay, that's the interaction. Omega is just a volume and VQ is the Fourier transform. And I remind you that we express this term, each term in the sum, we can represent by a diagram, which gives it some physical interpretation to the process involved in the interaction. And notice that the reason that we are summing over only 3 and not 4 indices is because in a system where there is translation invariance and the interaction only depends on the distance and not on the actual 2 coordinates, only the relative coordinate, if you like, and not the center of mass. And the total momentum is conserved, okay? The total center of mass momentum is conserved in any process, and that eliminates one of the k's, and it gives it this form. So if I represent it by a diagram, it looks like this. We imagine we are destroying 2 electrons, one with wave vector k and the sigma, spin sigma, k prime and sigma prime. So these are destroyed. Then this guy emits a particle with momentum q, and that particle is represented by this Fourier transform V of q, which can be imagined. Notice that this is a number, it's not an operator, it's a function of q, and it can be interpreted as an expectation value of the occupation of some kind of a gauge particle that is exchanged between the electrons, and that's what carries the electromagnetic forces. And it's actually the photon. Okay, so that's the field theoretic interpretation. Now, after this scattering, this guy loses. So this is what represents this creation operator. We are creating an electron with momentum reduced by q, but the other electron acquires the same q, so that the total momentum is conserved and also the spin is not changing. Okay, this comes from a density-density interaction, so the spin of each electron is not flipped in the process. So this diagram represents one term in the sum, and it gives it an interpretation. Okay, so this is an example for a two-body interaction, and now I want to make a Hartree-Fock approximation. What is a Hartree-Fock approximation? On the Hamiltonian, it's to take the interaction part and replace it by a form where I sum over all the possibilities to give two operators replaced by their expectation values. Okay? And we notice that in principle we have three terms, but one of them vanishes because of the it's an A dagger. This expectation value vanishes, and therefore we have two terms that remain. The first we call Hartree or direct, and the second we call exchange, and the exchange has the minus sign. Okay? So let's first write the I'm actually writing the full what I call V interaction Hartree-Fock is already the approximation. Okay? So it's the following. Let's keep the factor and the sum over k, k prime, q, sigma and sigma prime, vq. And now I have two terms. Okay, the first term is, let me use these colors to, I contract this guy with this guy, and I leave the other two as operator. Okay? What does it give me? So I get AK minus Q, AK sigma times A K prime plus Q sigma prime A K prime sigma prime. Okay? That's the first term, the direct. The exchange term is, or the Hartree, the Fock term is coming from contracting these two, okay? K minus Q with K prime. And leaving the other two as operators, and we pick a minus sign because we need to make an odd exchange between these two guys. So I get minus A K minus Q dagger sigma A K prime sigma prime. This is an expectation value, and then we're left with A K prime plus Q A and sigma prime and A K of and sigma. Okay? That's the first one, first term we call Hartree, and the second term I call Fock. Okay. Okay, great. Now let's write explicitly what it is, and I start with the Hartree term. So let's first talk about the Hartree. So okay. So what is it? I actually know what are these expectation values. I have a formula here. It's simply a delta of the indices. And notice that in our case, there are two indices. There are the wave vector and the spin. Both of them have to obey a delta. Okay? And then its delta is multiplied by the occupation of the state K sigma or whatever it is in the ground state, which is a full Fermi sea. In our case, it's a full Fermi sphere, right? Because we're talking about a free electron gas in 3 dimensions. And the Fock state, let me just mention it, that the ground state is a product over all K for which the absolute value is smaller than Kf, okay? And all sigmas of A, K, sigma acting on the empty vacuum, okay? Okay, so what is the Hartree term? So I'm replacing this expectation value by a delta. So first of all, let's look at the spin. This is very simple. In the Hartree term, we pair the spin with the same spin. Okay, the spin is the same, so I don't need to worry about it. But I do need to worry about the momenta. Here I have a delta of K minus Q and K, right? But when is this delta satisfied?
When Q equals 0.
For Q equals 0, that's right. So that's the same as writing delta of Q and 0. And therefore, it eliminates, so I no longer have a sum, after I apply the delta, I no longer have a sum over Q. I just have V of 0, okay? So let me write it down. Uh, 1 over 2 omega, and then I have V of 0. I can take it outside of the sum because it's just a single number. Okay. Now you may want to worry what it is, given that I think I already erased it, but V of Q for Coulomb interaction it's 4 pi E square over Q square, and what is it for Q equals 0? It's diverging. Okay. That's in the case of infinite system where Q is can take arbitrarily small values, then it's going to be divergent. But in practice, we'll talk about it, okay? But in practice, if you have a very large piece of metal, but still finite, then Q is quantized, and it will have some minimum value that we'll see in a minute what it is and how to interpret these results. But in any case, just formally, it is just one number that we can take outside of the sum, and we are left with two summation over two wave vectors, only two, K and K prime, and only sigma and sigma prime, and sorry, I didn't finish writing, because up front of this delta, I have the occupation n of k minus q of that state. But since q is 0, it's actually nothing but n of k, right? So I can actually write it as nk. I hope it's clear. Okay, it's just the occupation of the state with momentum k, where the occupation actually, yeah, and that's for a single spin. We also have to sum over spin. Maybe there are some factors of 2 that I'm missing here, so don't take it up to factor of 2. But so far it's okay. What I'm writing is exact. And what I get is just n of k and times whatever is left is, now it's an operator which depends on the indices k prime plus q, but q is 0 again, right? Q is 0. I enforce this delta over everything that appears here, and therefore it's just k prime and sigma prime, a k prime, sigma prime. Okay? Now actually I can, let me erase this because we know what we're talking about. Let me rewrite it in a slightly different way. So it's 1 over 2 omega v of 0. And now I want to separate this sum over indices to 2 parts. The first one I call, you see that I have actually something very simple here, because I can sum first over k and sigma, and then over k prime and sigma prime, and it's separable. It's a product of 2 independent sum. So I have a summation over k and sigma of nk. And we put it in brackets to say that this is just one number. In the minute you'll tell me what it is, and then what I'm left with is a k prime, sigma prime, a k prime dagger sigma prime, a k prime, sigma prime. Okay? Now let's interpret what we have here. What is this thing in the brackets? It's
just the number of particles.
Exactly, exactly. This is nothing but the number of particles. Okay, and it's a number. Okay, it's already just a number of particles, and the operator that I couple to is also a sum over all the wave vector, all the sigmas of something that is nothing but the number operator. But here it's a number of, this is the number operator, k prime, sigma prime, and if I sum over all the k primes and sigma prime, all together, what I get is just the number operator, right? Okay, so it is actually very simple. So what I get is, notice that this, first of all, this Hartree term is huge. It's very large. Why is it very large? In fact, in the infinite system, it's not even well defined because it's diverging, because v of 0 is infinite. In a finite system, let's be a little more careful. in a finite system, let's say that I have in 3 dimensions, I have L by L by L. This is a cube of size L, and L is very large but finite. Omega, the volume, is L cubed, right? Q0, let's say, the lowest value of Q allowed is not 0, it's 2 pi over L, right? So V of 0 divided by omega, actually maybe let me write it a little closer because I'm not sure if you can see it. Let me do it here. So this term, if I'm keeping track of a finite size, is going to be something that is proportional up to a number to let me keep the 1/2 for a reason that you'll see soon, and the number v0 over omega is scaling like E square over L. Okay, right? Because I have L cubed and L squared. That's what it is. That's the right unit, right? So how can we interpret it? First of all, we see that we get, this is an effective Hamiltonian term that looks very much like a single body Hamiltonian. And what does it do? It adds to the energy epsilon k for each k state, for each particle. I'm replacing the energy by epsilon k plus a constant. What is this constant? It's this factor times the n, capital N, which is the total number of particles. So what does it actually describe? It describes an interaction of each electron with the entire charge of the whole electronic system. Okay, so this is the physical meaning of the Hartree term in our case. It's describing a mean field where each individual electron sees all the other electrons as one huge chunk of a negative charge and repulsively interacts with it, and it adds a huge energy scale to the problem, and it would be a disaster unless there was a positive background. And because we are talking about electrons in a metal, it's compensated by the positive charge, right? Which is exactly equal but opposite in sign, all right? And therefore, although the Hartree term in this particular case is huge by itself, we have to remember that we're also subtracting a very large background, and together it gives 0. So it does nothing, okay? Okay, it does nothing. But if you just want to focus on it as it is, let us see how can we interpret the leading correction to the energy, if you like. So the leading correction to the energy will be the expectation value of this term, which will replace n hat with capital N again, which is just the total number of particles. So what will be the expectation value of this, which is like first order correction to the energy? it's going to be, let me deliberately write it a little differently, 1/2 En square over L. What is this? Can you recognize it from your... Didn't hear you.
Brody model.
No, it's a term in the energy that is proportional to what is electron charge times N.
It's a total charge of the
Total charge of the electronic system. And it's squared, right? So we can write it as
Just the Coulomb interaction.
No, it's all coming from the Coulomb
but
interaction, but it's
like the classical version.
yes, and it's actually just an energy of a capacitor, right? You remember? Right? So, and the capacitance is actually just the linear size of the system. It's a capacitance of, if you have a piece of metal, okay, maybe it also depends on the geometry, but if it's just a cube, like in our, then it's like we have a huge capacitor, and this is the energy of the capacitor. But again, it's compensated with a positive background, so it's actually not contributing anything. Okay. So to conclude, the Hartree part of the interaction is not important. It's not always true, but it's true in this case. The last thing I want to say about it, before we move to the exchange term, because this is really the interesting correction, let us describe it in a diagrammatic term. And here is the following convention. When I plot this diagram with the arrows open-ended, this refers to an operator. If I want to turn it into an expectation value, the graphic representation of it is to do a contraction, okay? Let's apply this operation of contracting two operators. What does it mean to contract? It's, in our case, is to short circuit or connect together two of the legs, okay? Now, in the case of the Hartree, what you're doing is contracting these two with these two. And we notice that because it's just the same, this arrow describes a particle that is created and then annihilated, but it's the same particle. So it must obey a delta. The momentum cannot change along it, right? So it's only meaningful if Q is 0, okay? So when Q is 0, and this is replaced by, so let me not, I want to leave the diagram, so I'm not writing it here, but this is, no, so it's minus Q. Minus Q. Okay, so let me draw the diagram that I get from this. And this is a diagram that represents actually the expectation value. So it's basically a bubble. Well, this is K sigma. Here I have a wiggly line V of 0. And there is another wiggly line, another closed loop of K prime and sigma prime, okay? And it's actually, sorry that I erased it, so let me write down the expression, so it's this expression is up to, okay, there's an overall prefactor, it's V0 times n squared. That's what it is, okay? So you can identify the connection with the diagram because V of 0, this is this, and the n square is just a product of these two loops because each of them describes a dagger k ak sigma, which is just the occupation of a state with k and with sigma, and if I, after summation over all the k's and sigmas, I just get n. And this is exactly identical, right? Only I changed the name of the dummy index, but it's the same. Okay? So this is a graphic representation of the mathematical expression. Right? Is it clear?
Do we know the physical meaning?
The physical meaning is exactly this, that you have, I mean, the diagram is just breaking the process of interaction into a process whereby an electron of momentum k emits a photon and remains with a smaller momentum, or momentum k minus q, and then this photon is absorbed by another particle and changes its momentum so that the total momentum is conserved. But for q equals 0, for the Hartree part, you get an expectation value only for the case where q equals 0, okay? And the q equals 0 state actually describes each disconnected loop times another disconnected loop. What is this disconnected loop? It's just describing the number of, each term like this describes an occupation of an electron in the Fermi sphere, and summing over all states give you just the number of particles. So it has a very simple meaning. As we said, it's like the total charge or the total number. Okay?
Is it really, like, in reality, it's actually describing reality, this approximation?
What do you mean?
I mean,
you're asking whether the approximation is good.
yeah, whether it's
That's
actually agree with
we'll get to it. Okay, so as I said, let me backtrack a little. What we are doing is we take a full interaction term and replace it by an approximate form. This is an approximate.
Yeah, but how good is the approximation?
Oh,
that's what I'm asking.
so you have to ask yourself what are the corrections, and the corrections are obviously we will, I hope, get later to how do we quantify them, but let me tell you what you're missing. So you have things like this. You are replacing the product of two operators by their expectation value. What are you missing? You're missing the difference, right? So, and this, if you like, it's some kind of a delta of, it's basically the deviation of the operator due to quantum fluctuations from its expectation value, okay? Now, whether it's small, it's not clear. You have to go to the next order in perturbation theory and quantify it, okay?
Because intuitively, maybe I didn't really got it, but it seems that every state of electrons is kind of disconnected from other states, because it's always q equals 0, and
No,
they don't really...
Yes, but this is only one term, Okay.
Mm-hmm.
There's
No,
this.
and it's all of the terms are like this. We have a.
No, I'm saying, but this is only the Hartree term. We still didn't get to the Fock term, which is the more interesting part.
Okay.
But the question you really have to ask is, how small is this?
Yeah.
Now, why is before I close the loop and all that? Why? What am I missing in this approximation? I'm missing the fact that look, it looks like this electron emitted a photon in general. Okay, for general Q, an electron can emit a photon and exchange it with another electron. Okay, this can happen at any point. So maybe this electron, after being emitted, will now emit another photon and will split to a different momentum. And this can happen infinitely many times, right? So if we want to get the exact expression, has actually a diagrammatic representation in terms of an infinite series of processes where at each level in the each level in the approximation, I'm emitting a larger and larger number of photons. Okay, it's like a power series, if you like, in V of Q.
Which means we can calculate it.
Now later I'll show you a clever way of doing it, but once again we'll have one. Look, the exact problem is not tractable, but there is some very effective approximation you can do. But what we are doing now is just the first order. Okay, in fact, it's really first order in perturbation theory. The second order can diverge, who knows? We'll have to check, okay? Okay, so, but obviously, if the interaction was small, just, you know, if it's a very weak interaction, usually you believe that the approximation is under control, okay? Right, because altogether, the exact result is a power series which has a parameter, the interaction to some power, and if it's small, it's going to be decaying, okay? And that's a question, whether Coulomb interaction is small. And the answer is, as you'll see soon, no. Okay, but let's not jump ahead, okay? But the question is very well taken. So far I just talked about the Hartree part, okay? And the conclusion is we can throw it away. Let's look at now the exchange term. And also erasing this red color because then we'll have to draw a different diagram. Okay, so okay. So that's really the interesting part. Let me copy it. I call it B interaction F for Fock. And it's given by the second term here. The second term has an overall minus sign. Let me take it outside of the sum, so it's minus 1 over 2 omega, and now I have a sum over k prime and q of and sigma prime, and now I'm using this contraction. What is it? It's just the occupation of K minus Q and sigma times a delta. What is the delta? So it's N of K minus Q and sigma. And now I have a delta. Actually, I have two deltas because sigma and sigma prime are not necessarily the same. So I have to enforce sigma prime to be equal to sigma. Okay, and notice that then I don't have a factor of 2 on the sigma prime because it has to be exactly the same as the sigma. And there's another delta which equates K minus Q to K prime. Okay? Okay, and now K prime, because K prime, so the delta actually forces K prime to be equal to K minus Q, and Q doesn't have to be 0. And now I have a V of Q, which I forgot to write, so let me add it here. V of Q, right? Q is still anything because I'm summing over. And what I'm left with is, let me just continue, is the operator. And the operator now is, let's already apply the delta, okay? To avoid using too many indices. So this K prime has to be equal to K minus Q, right? So K prime plus Q equals K minus Q plus Q. In other words, it's just K. And also sigma prime equals to sigma. Okay? So that's what I got. And because of the deltas, I can eliminate two indices, sigma prime and K prime. So let me rewrite it. It's a minus 1 over 2 omega, and sigma of Q, I deliberately, no, sorry, let me write it like this. So it's a sum over K and sigma. Sum over Q, I deliberately separate the summation over Q of, what do I have inside the sum over Q? I have V of Q and N of K minus Q and sigma. And all that, which I can put in brackets because it's just the summation over Q, but still depends on K, is multiplying A dagger K sigma, A K sigma, right? Okay, now let's understand what we got, because if we compare this to H0, H0 is the kinetic energy, just the usual thing where I remind you also that we're assuming that epsilon K is just the usual kinetic energy, parabolic band. Okay, so after summation over sigma, what we get here is, oh sorry, not over sigma, after summation over Q, and also multiplying by this prefactor, what I get is a correction to the energy epsilon k, right? So let me call all of this let me call this delta of k. Okay, it's some function of k. Okay, some function of k. In terms of delta, I get that the Fock contribution to the interaction is minus sum over k and sigma delta k a dagger k sigma a k sigma. So what is the Fock term doing to the energy, or to the Hamiltonian, in fact? The Hamiltonian doesn't change its general form. It's still of the form that you have some corrected single body form, but all the energies epsilon k are shifted down by some function delta of k. And what is this k? You have to solve an integral over q. I mean, that's already a technical point. But the important thing is that the Fock term of the Coulomb interaction, because of the minus sign that has to do with the fact that the electrons are fermion and the Pauli exclusion and all that it infers, the energy is reduced. We have a repulsive interaction, but it reduces the energy. Okay? And that's the effect that actually allows for correlations like the formation of ferromagnetism I mentioned and all that. Okay, so out of a repulsive interaction, the conclusion is that on the level of the Hartree-Fock approximation, first of all, it doesn't look like we're changing the nature of the ground state. We're just shifting the energies by something. And for a repulsive interaction, we actually get a negative correction, okay? Because the positive part is large but cancels, okay? In a neutral background. So, okay. Now let's understand it. Let's describe it diagrammatically. So what I wrote here is a term in the Hamiltonian, and for each k, the energy epsilon k is shifted to epsilon minus delta. The expectation value is just resulting from taking the expectation value of this thing, and the expectation value is nothing but the number. So it's going to give you sum over k of nk times the number of particles, right, the occupation of the Fermi sea, and it just adds to the kinetic the total kinetic energy of a field Fermi sphere is just the sum over all k up to E Fermi, okay? And the correction, this negative correction, gives you just the sum of all k of delta up to k Fermi, okay? That's all. So it gives some overall correction to the total energy. And the total result, the total correction is negative because delta is by definition positive. Okay? Okay, so how do we describe it? Diagrammatically, sorry, this is Fock, the Fock part, expectation value is described by the following diagram. Now I'm again closing, I'm imposing this delta, by closing legs. Okay, which legs do I close? Here it's actually plotted not very conveniently because I'm contracting k minus q with k prime, so I have to take this loop. Okay. Okay, and then to get the expectation value, I also contract this loop. Now it looks very funny, it looks complicated, but let us rotate let us rotate it. I don't know if you can see that topologically it's equivalent. I mean, it would be if I plotted the legs differently, but you can always rotate the legs, right? It's just a drawing. It's equivalent to the following diagram. There's a V of Q, where Q is in this direction, and then I have one loop going this way, and it connects so it's k minus q and sigma, and another loop which is k. Okay, this is k. Then so this is what it describes. So there is a particle, an electron with momentum k. It emits a photon, and there it remains with a momentum k minus q, but then it absorbs it again and returns to itself. Okay, so this closed loop is nothing but ak minus q, ak minus q with an index sigma, which is nothing but the occupation of k minus q and sigma. And this line is similarly n of k and sigma. Okay, the sigma is 1 sigma. And this is V of Q. Okay? So the total contribution after summing over, and of course I have here a summation over all k and q and sigma. After summing over all these diagrams, what I get is just the expression I wrote here, which is okay, let me rewrite it again. I have to erase something. Don't need this anymore. Okay, so it is given by up to the factor of 1 over 2 omega, which I keep carrying outside. It's a sum over k, q, and sigma of V of Q. So again, you see, you can interpret the picture, the diagram very simply. It's a product of 3 things: VQ, NK minus Q, and NK. Okay, that's all. Okay, and if you first perform the summation over Q, you'll get my definition of delta. Okay? And that's already a closed expression, which if you now plug in the Coulomb interaction and turn the sums into integrals, and you do some complicated calculation, you get a result. Okay? The important things to keep up, and what I forgot something very, very important, a minus sign. Okay, so all this comes with a minus sign. It's a negative correction. Okay? Okay, so is that clear? I mean, it's a bit technical, but it's straightforward. Let me summarize what we will get from it for characteristic metals. If I now take the Hartree-Fock approximation, I'm now erasing all that and writing the so the total let me see, do I want to do it per electron? Yeah, let's do the total kinetic energy, okay, per electron. What is it? It's made out of, sorry, the total energy. Within the Hartree-Fock approximation is a sum of two terms. The first term is kinetic energy, which I will write in a second. This is something you know from your undergraduate statistical mechanics, or solid state, plus exchange energy, which is the correction that we get from the Fock term of the interaction. And let's write down the final result. The kinetic energy per electron, I hope you remember, but if not, I remind you, is 3/5 times E Fermi. Remember that? Okay, this is in 3 dimensions, of course. Where E Fermi is h bar square kF square over 2m. The exchange energy is minus something, and this something is, you can write it as some number, which is not so important, times E square times kF. Okay? Okay, great. So, and now what we believe that our approximation is equivalent to doing the first order in perturbation theory. Okay? So we have to ask ourselves whether the correction is small. When is perturbation theory good? When this should be much smaller than this, right? Okay, let's compare. So in the literature, it's customary to define a parameter called Rs, which is defined as, let's just define it as the interaction energy, the Coulomb energy, which is represented by this exchange term divided by the kinetic energy. Okay? Okay, let's see what it is. So, and I'm only making, I neglect here factors of 2 and pi and all that. Let's just look at the scale that comes in. So it's E squared times Kf divided by the kinetic energy, which up to a prefactor is just, I already erased it, but it's h bar square Kf square divided by 2m. So let me put the m here. Okay, and the factors of 2, I forget it. Okay? Okay, let's rewrite it. It's E squared. Let me just make sure. Yeah, okay, that's E squared times m over h bar square times, you see the Kf cancels once, and I get 1 over Kf. Okay. Now, okay, and now remember, what we want is this factor to be much smaller than 1. Okay. Now, what is K Fermi in metals? It's about inverse of an angstrom, right? So it's of order the distance between the 1 over the distance between atoms, right? So, or the distance or the average distance between electrons. Okay, so Kf goes like 1 over R naught, where R naught is the typical distance between 2 electrons in a metal. And this factor, there is something that is called the Bohr radius, which is exactly the same Bohr radius that appears in the hydrogen atom. If you remember, this is what it is. It has units of length, and how much is what is the radius? It's actually the radius of the hydrogen atom. What is it? Half an angstrom, right? If you remember correctly. So what I wrote here is the ratio between the distance between electrons to the Bohr radius. And it is, in metals, of order 1. Right? Now, if instead of a metal, I'm talking, yeah?
K is momentum related. Kf.
Kf is the Fermi momentum. The Fermi momentum is inverse.
So if you look up, so it's not unitless, this thing.
No,
right?
no. This is 1 over.
1 over distance, and the other
And
one.
Kf is also, so Kf is 1 over R naught. That's why R naught is in there. Kf, 1 over Kf is R naught.
It's units, you divide here units of.
It must be dimensionless because I started from energy
Yeah.
over energy. This is length.
Okay, it's because we neglected the. Okay.
No neglect. I mean, I only neglected numerical prefactors, but okay, but the units are all right. So it's just a ratio of, as I said, the distance between electrons, the average distance, and the Bohr radius. And in metals, it's of order 1 or 2 even, if you like. If you're talking about materials that are not metals, like doped semiconductors, where you have a band, a parabolic band with effective mass, and some Fermi energy. Usually the Fermi momentum is even smaller, which makes the distance between electrons even bigger, which makes this factor larger than 1. So perturbation theory on the naive level is not justified. Coulomb interaction is strong, okay? Although the kinetic energy, E Fermi is also a very large energy scale, but the ratios is of order 1 in the real world. And that raises a question, because we know that actually it is true that metals are very well described by free gas, right? I mean, the Drude model, all that, it works. Maybe it breaks down for more complicated materials, but not for metals. So perturbation theory does work, but it doesn't work because of naive reason that the first order is small. The reason that it ultimately works is if we sum over the corrections, the higher order, magically will converge to something small. And the physical reasoning for it is the effect that we call screening. Okay, so just to understand why is it true, you don't need to do the calculation, although I hope at some point we'll do it. It's actually very cute and not so complicated. But physically, it's coming from the fact that a metal is a state of matter where the particles have a lot of kinetic energy. They're very mobile. And what happens if you have a lot of electrons, and on the average they have some density. Now you throw in a test charge, like what we do in electrostatics. You put a test charge, and it doesn't matter if it's positive or negative. Let's take positive impurity. What happens when you throw a positive charge to a medium where you have mobile particles with negative charge? They will be attracted to it, right? So you're going to get a cloud of electrons that bunch around this positive charge, and as you go away from it, the density, this accumulation decays, okay? So this effect is called screening, because the negative charge screens the positive charge. And by the way, if you put a negative charge, what happens? The electrons will be pushed away from it, and you will create a cloud of positive charge, right? Because the positive background will dominate. So as a result, the effective charge of this, if you calculate it, and this is, you can do the calculation quantitatively, you can show that beyond a length scale that is denoted by lambda is called the screening length, and it's very, very short. Beyond this length, the effective charge is 0. Okay? And the screening length is in fact of order 1 angstrom again. Okay, it's very short. So that's why metals Coulomb interactions are not effective, because the bare Coulomb interaction that is represented by this 1 over q square is actually corrected to a screened effective interaction. But to get it from a calculation like what we did here in a systematic way, you have to sum over an infinite series. And magically you get a formula, a closed formula that is simple and gives the right physics, okay? So that's something to keep in mind, but you see that the tools that we got here, the basic tool is that we know how to compute expectation values of operators, and I also showed you a diagrammatic language that is going to be very useful if you want to account for higher order processes. Okay? So you don't even have to write the mathematics expression, just the diagrams. And you already can translate it into an expression. Okay? So maybe we'll get to it later. So, okay. Questions? Before I say so, I have 15 minutes which I want to devote to just to give you an introduction to the next subject, which I hope to cover next week, unless you have a question. Because, yeah?
You said that somehow we can, from calculations, we can derive a new term that will compensate the Hartree term, right? And
no, we don't have to derive it. We know what it is, because again, on the level of the Hartree, you are basically, it's a very brutal mean field where you replace all the electrons by a chunk of negative charge. Okay, and your particle, each electron interacts with this chunk. But you are in a metal. You also have positive charge coming from the ions. The material is neutral. So on the same level of the mean field, the electron also interacts with a big chunk of the positive charge of the ions. And the fact that the ions are, okay, it's actually a crystal, these details are averaged out because the electron is, the wavelength of the electron is I mean, it's an extended wave over the size of the atomic scale. So on the level of this Hartree approximation, you get plus and minus the same thing, okay? Because the total charge of the ions is equal in magnitude and opposite in sign to the total charge of the electrons.
yeah, but I mean, in our model, we didn't take into account any ions.
No, but we know that they are there. Okay, that's why I'm saying. I mean, the model you get, the Hartree term, you can calculate it. Okay, I didn't avoid calculating it. I'm just saying that we know that there is something else we didn't account for, and we actually know what it is. Okay, and that's why it doesn't contribute anything. Okay. Okay, so the last thing I want to say is I just introduced here and this effect of the screening that is actually very intuitive, and it builds on the fact that the electron gas state has a high kinetic energy, and you can move around charges, so they can screen any perturbation. That works very well in 3 dimensions. In 2 dimensions, actually it's also there, but it's much weaker because you have less degrees of freedom. If you do the mathematics of the screening effect, it actually gives a power law instead of an exponential. It's not as good, but still okay. If you go to 1 dimension, there is a dramatic problem with this physical argument. So what in 1 dimension, you have your electrons and they can only move on 1 line, right? Now you throw in an impurity, and they want to screen it, but you know there's no place to move, right? I mean, they can.
But it's not a physical system, right?
No, of course it is, because in the lab you can accumulate wires. You can create, and people do that for a long time. It's not even new. You can create in a semiconductor device by applying gate voltages and all that. You can create a channel where you lock the electrons in the two dimensions. You lock it in one quantum state, and then it has only 1 degree of freedom. So it is one-dimensional, okay? So, and there are also other examples, like for example, there are materials that are called conducting polymers, and they are made of chains that are very weakly coupled, and along the chain, the charges are free to move, and it's like a one-dimensional channel, but very weak coupling between. Okay? So in reality, there are such systems, and you can already see intuitively that the screening may not work so well. But on the other hand, if you have some charge disturbance, some impurity that you throw, so first of all, any impurity in 1D will be very effective because, again, there's not much freedom. You can only go scatter forward and backwards, that's it, right? There's not enough degrees of freedom. You can, however, show, you can imagine that there can be, that maybe because of the interaction, such a disturbance may cause a propagating wave where you create essentially deformations of the electron density. This is actually called the plasmon, if you like, if you heard the, right? There are charge mode that can propagate, and it's collective. It's made of contracting and expanding density of the electrons with compared to their average value. And it turns out there is a trick, a mathematical trick, by which you can forget about the electrons and replace it by new degrees of freedom that describe this mode. Okay? So we'll very briefly introduce the model that applies it, and it actually takes advantage of the one dimension and does some mappings that you cannot generally do. Okay? It actually, in a sense, it makes it much simpler, but this is a case where treating the interactions perturbatively is the wrong way to start, and what you can do is something much nicer. It's to change the definition of your elementary degrees of freedom, and if you are able to do it and describe the system in terms of free particles of a new kind, then the problem is solved. You know everything you want to know about it, okay? So this state of matter is called the Luttinger liquid, and we'll discuss it, I think because of the time, I'm getting tired. Let me not start doing calculations, and we'll do it next week, okay? And we'll just do it in a nutshell, because I don't want to devote too much time to the details, just to show you a trick which takes advantage of this algebra of the second quantization. So it's also a practice of the method.
So we'll use kind of the same approach as we did for phonons.
So in the end, so what we are going to do is a mapping of the interacting system to something that looks like Hamiltonian of phonons. But these phonons will be these plasmons.
Yeah.
This is their physical interpretation. Okay? Okay, so stay tuned.
Thank you.
ביקשתי ממך או מקורס אחר, אבל יש מצב שאחרי שאנחנו מגישים את השיעורי בית, אז יעלו פתרונות שנוכל להשוות?
אני פחות אוהבת לעשות את זה, כי...
בשביל שלא יעבירו כאילו...
לא, האמת היא ששר, אני חושבת ששר כן מפרסם באיזשהו שלב, אבל אחרי איזשהו... אני חושבת שהוא כן מפרסם אחרי איזשהו...
תדבר איתו?
תדבר איתו, בסדר? אני לא זוכרת, כאילו, באיזשהו מקום אני לא זוכרת שמפרסמים פתרונות. יותר מדי נגיש, ובעצם, אתה יודע, עדיף, תקבע פגישה אם אתה כאילו לא ברור לך, גם אני מקווה שהוא בודק את התרגילים, אז הם לא נותנים ציונים כאילו לא מורידים על טעויות, אבל יכול להיות שהוא כותב הערות.
סתם בשביל לוודא כזה, את יודעת.
כן, ברור. לא, ברור, אבל כן. אבל נדמה לי שהוא כן מפרסם פתרונות.
אני אשאל אותו, תודה.
טוב, שבת שלום.